So welcome all. Thank you very much for joining. So the idea is to have a series of very short presentations, a couple of minutes, just highlighting some examples of SHEAR projects and activities that have done relevant activities in the broad space of co-development of tools and methods to support decision making. We'll keep them again short with the idea of afterwards having plenty of time for discussion, questions, but also anyone who participates and who has had similar experiences which they're keen to share. Please feel free to do so. So it's really an opportunity to take it beyond the list of speakers and basically a bit of a soapbox opportunity to stand up and tell a bit about what you've been up to in the context of SHEAR. And just as a very quick, if you will, theoretical background, although the title says co-development of tools, I'd like to broaden it up a bit and look at co-development and essentially any approaches that really try and get locally relevant, actionable knowledge. I think in the end, that's what SHEAR is about, leveraging science to provide decision makers with the best knowledge and information to make appropriate decisions in the context of resilience building to landslides and flood risk. And that's a very broad area which basically touches upon the idea of generating the best evidence and leveraging science to support evidence-based decision making. And that ties a lot, so relates to basically the way that we generate knowledge, basically the fundamental process of science, generating new knowledge from data collection, collecting raw evidence in the field, raw observations, to processing that, extracting knowledge from the raw data, to sharing that, disseminating that, interpreting that together with people that have to use that evidence. And that is very much a circle in the sense that that process of sharing and discussion is also the process where knowledge gaps are being identified. So it's also a starting point, if you will, of the next cycle of knowledge generation, identifying really what are the bottlenecks that prohibit or prevent making the best decisions in the context of resilience. So that then starts again that process, and basically that is a continuous cycle, a virtuous cycle, if you will, of increasing knowledge, but also ensuring that that knowledge is locally relevant and actionable, usable, and effectively used. And that's a bit the theoretical framework that I'd like to pitch and help with structuring your ideas and requesting, eliciting input from and ideas and discussion from all of us. And so we've got a couple of presentations to start off with, but I'd like to ask the presenters to keep things short so we can afterwards discuss and hear from other people in the audience about similar or perhaps contrasting experiences and ideas. And that's all for me. So I'll now pass on the word to our first speaker, Ting from the University of Reading. Ting, the floor is yours.
Okay, can everyone see my screen?
I do, but you might want to put it in full screen.
Okay.
Yeah, there you go.
Yeah.
Perfect.
Okay, thank you very much. Okay, so good afternoon, everyone. I'm Ting Song, currently a NERC Independent Research Fellow based at the Department of Meteorology, University of Reading. And today I'll talk about our multi-scale mapping work in Sri Lanka on behalf of our COSMA team led by Dr. Zhiwen Luo, Professor Sugrimond. And before I get started, I'd like to acknowledge our team members, Xiaoxiong, Louis, and Hamid, along with others who have contributed significantly to this work. The overarching question of our COSMA project is how to build resilience to heat extremes in Sri Lanka. Sri Lanka, like many other South Asian countries, is characterized by hot, humid tropical climate, experiencing intense, frequent, and long-lasting heatwave events. and such humans are at a high risk of temperature-related mortality. The way we approach this research question is from two angles. First, from the climate perspective, we investigate how urban form would influence the outdoor microclimate. Second, we incorporate expertise from architects and building physicists to understand the impacts of building design on indoor thermal environment. And such, in the COSMA project, we design a multi-scale urban climate modeling framework and shown in this flowchart. First, we collect detailed urban information such as land cover, human activities, etc. Then we incorporate this information into a state-of-the-art urban land surface model, SHEAR, to conduct fine-scale urban climate simulations to map the outdoor thermal comfort. Meanwhile, we are coupling SHEAR with a building energy model. Here we use Energy Plus to allow detailed modeling of the indoor thermal environment. In the next two slides, I'll focus on the outdoor thermal comfort mapping and give you a quick overview of some other key results. So when we talk about thermal comfort, we need to bear in mind that thermal comfort is more than temperature. In addition, it is also influenced by humidity, wind speed, radiation, etc. So here, we adopt a simple but widely used indicator, apparent temperature, to investigate the spatial characteristics of thermal comfort in Sri Lanka. And this formulation indicates the higher the apparent temperature is, the poorer the thermal environment condition will be. And also, and as we can see from this formulation, the apparent temperature is positively related to air temperature and the vapor pressure, while negatively correlated with wind speed. Then, using the SHEAR simulation results for a 3-day heat wave period in Sri Lanka, we produced the thermal comfort maps shown here. From the left to right are the maximum, mean, and minimum apparent temperature of our study area, centered in Colombo, the capital city of Sri Lanka. In these maps, we can clearly see that we can identify several hotspots with high overheating risks indicated by the apparent temperature. Next, I'll zoom into one particular area with high apparent temperature to understand the determinants. The results here are for 10 grids with the highest apparent temperatures in the previous slide. The left bar chart shows their land cover composition. In this bar chart, except for 3 grids, we can see that almost all the grids are characterized by densely built up areas represented by the grayish bars. This bar chart suggests that the densely built up areas are actually vulnerable areas, might be the most vulnerable areas to heat waves with respect to outdoor thermal comfort. However, it is also interesting to see that the grids with relatively large water surface shown by these blue bars were also undergoing poor thermal comfort conditions. So we decompose the apparent temperature to understand their meteorological determinants. Now let's look at this bar chart on the right-hand side. In this bar chart, the contribution to apparent temperature from air temperature, vapor pressure, and wind speed are indicated by the orange, blue, and the green bars respectively. Overall, we can see the temperature dominates the contribution to apparent temperature. Then we found for the 3 grids with relatively large water surface coverage, the contribution of vapor pressure is remarkably larger compared to the other grids, implying excessive humidity may worsen the thermal comfort on the heat waves. The above is just a quick overview of our work on thermal comfort mapping in the COSMA project, which I hope might give you a sense about our efforts in enhancing the resilience to overheating risks in Sri Lanka. Besides, supported by the COSMA project, we have published several papers and more are in pipeline. If you'd like to know more about our COSMA research, please have a read. Okay, that's all. Thank you.
Great. Thank you very much, Ting. We won't take any questions now, with the idea of first having the presentations. So if any questions have arisen, please do keep them, and afterwards during the discussion, obviously you have the opportunity to ask questions to any of the the speakers. So thanks again, Ting. If you can stop sharing, then I'll invite the next speaker, Emma Mwangi from the University of Sussex. So Emma, feel free to unmute, share any slides you may have. There you are. I can see you. I can also see your screen. So yeah, right. Ready to go. Over to you.
All right, thank you very much. Good morning, good afternoon, everyone. My name is Emma Mwangi from the University of Sussex, but previously working with the FOPAC project in Kenya Red Cross Society. And today I'll be talking about the FOPAC efforts to co-produce decision-relevant focused products in Kenya with the stakeholders within the study area. And FOPAC really had two major aims. One was to improve the focus, but besides that is to look at how do these focus get integrated in flood and drought early warning systems. And today I'll be talking about the work we did with the existing drought early warning system in Kenya, and in particular in Kitui County, the county you can see marked purple on the map. And like any other co-production activity, or when you're wanting to improve things for people, one of the key things we started with in our approach is to engage with the existing drought early warning stakeholders for us to understand, one, how is your system working? Were they using climate information in it? And if not, what were the challenges? And one of the things that we learned while engaging with them is that there was an elaborate drought early warning system that has had these particular classifications that have just popped out. And you can see that to move from one classification to the other. So for example, from a normal situation to alert, you can see there are indicators we're using, for example, the standardized precipitation index and the vegetation condition index. And what we learned by just interrogating and involving the stakeholders is that, one, this particular system was quite responsive, just using monitored climate information and socioeconomic data. The other thing is that within the year, the system, there are other activities that are done with within the system. For example, looking at the rain season. After the rain seasons, they assess what's the cropping like, the market like, and all that. Then they also have contingency planning. But then if you look at the provision of climate information, especially for the season, it doesn't match up with a lot of those activities. And just from this entire engagement, then we learned, one, information wasn't systematically being used with the system, and because of two major reasons. The information was not in the right time, as you've seen with these stars, the yellow stars. And then the metrics that was being provided, the information that was being provided was of rainfall, whereas their system was using indicators like VCI and SPI. So what did we do then moving forward? One of the things was to look at the system again and see how can we then produce information that is able to support all the decisions, but also within the timelines and within the indicators that they use. And therein came the co-production of the decision relevant focus products that then we started providing SPI and VCI for this particular drought early warning system. But then, as we all know, in decision making, as Pablo has just been showing us, it's also about the skill of the focused system. How often does a system get it right or get it wrong? Because that also means that people are making decisions with skill information at hand, more informed of what investment they should be making. And lastly, we piloted this, not just producing it, but piloting it with them over 2 seasons. We started with one particular county, then this was scaled up to 7 counties. And one of the things we did was not just give them the information, but capacity build on how do you interpret, how do you use this in decision making, what kind of actions are you able to do with this? And most importantly was to enhance the link between the stakeholders who are users and the meteorological services who are producers. And lastly, just also looking at the system, how do we move then from this responsive to an anticipatory system by introducing another classification that looks at just the forecasted information, not just moving with the monitored information. And this has really been advocacy so that it is sustainable, and when it changes, then there is that ownership. In summary, really, one of the successes that we've seen with this co-production is that this information has now been scaled up. 7 of the 23 counties are using it in monthly bulletins. Institutions, mandated institutions, have taken up the production of the information, and we've also seen capacity strengthening the engagement between users and producers. But that doesn't stop there. What can we recommend going forward is that co-production, that co-development is quite intense, needs a lot of time, needs enough funding, and it also needs that coordination and links between producers and users are enhanced, because it's only by talking that you get to understand what exactly is going on. And lastly, it's about capacity strengthening. I cannot come and start asking you questions about your process if I don't understand what kind of questions as a scientist I would be asking. Thank you very much. So further information can be found in those links.
Well, thank you very much, Emma. That's great, and I've got lots of questions myself, but again, we'll keep them all for the discussion afterwards. So thanks again, and then we'll move on to our next speaker, Jeff Neal from the University of Bristol. Jeff, feel free to share your screen. There you are. I don't think we can see you, so feel free to switch on your video as well, or without, as you prefer. In any case, the floor is yours.
Thank you, Wouter. Thanks everyone for listening to this talk. I'm going to talk today a little bit about the flood hazard mapping that we did with the University of Kinshasa in the DRC, and how we put that onto a web platform. What I thought I would do was just a little bit of background on the science first. We've been mapping exposure actually with a global flood model. This is essentially a model that takes information on kind of catchment characteristics regionally, puts them through a river routing model, and then estimates return period flood hazard. Our current model goes down to 30-meter resolution. And here in this slide, you can see an example of the model output for 90-meter resolution, 1 in 100-year flood plain results across Africa. So here we see the flood depths that we'd expect to be exceeded once in 100 years. And part of the project was to develop this model a little bit more, and another part of it was to have a go at disseminating that information into use cases and see how it might be used. Just to give you a context of the development also that was going on at the time. So this is our, for a location in Zimbabwe, this is our model that we had in 2015. So this is the pre-SHEAR global flood model output that we had for this particular location. It's a 1 kilometer model downscaled to 90-meter resolution. As part of the SHEAR, we did an update to this model. We improved the elevation data and various other things, and that gave us the simulation that we had here in 2019. These are the results that we actually used in the DRC then with the partners in Kinshasa. But actually we continued to work on the model after that, and this is the latest incarnation. It's a 30-meter model now. And what you can start to see here is some of the kind of floodplain features that you might expect to see, such as kind of meander cutoffs and other things on the floodplains. With this model, we also start to look at pluvial flooding, given the resolution and the accuracy of the vertical data. So here's then, if you like, a flash flood layer added on top of that same model. So more importantly, what did we do in terms of the kind of co-production of some useful information from these data? But I think it's useful to think about the starting point that we had. So we initially had a previous collaboration with the university on another project funded by the Royal Society, where we'd held a number of stakeholder workshops in Kinshasa, and we'd spoken to the local government, the water resources agencies and others, and we got an idea of some of the range of hydrological issues that were affecting the DRC. And one of them was a lack of knowledge on flood hazard and which parts of the DRC were hazardous. There was perceived to be a lot of risk, but no one really knew where it was. This is me here, and this is Raphael, my main collaborator in the DRC, in the second photo. So we started the project by doing a number of pieces of research work together, working with a university. Obviously, it was relatively easy to speak the same language in terms of how we might go about the research. We did some work to evaluate the modeling that we'd done, get an idea of the quality of the data and what it might be useful for, and that we published in ERL. And then also on the kind of co-production side, Godot Ballo and Raphael led a piece of work where we did a flood hazard and risk assessment across the whole of the Congo Basin, and produced statistics and various bits of information from that. Was actually then presented in an AGU monograph. Once we had this information, then we set about thinking about how we might disseminate and share this information. So we ran a number of training events where we designed some training material, which is basically a GIS analyses that people could do to look at these data. And we delivered that in Tanzania, Burundi, UK, and the DRC. And also the University of Kinshasa then led the development of a web platform where they extracted some basic kind of catchment information from the data set that we had, and put it on a portal where people in country could access the information from government or from the rivers authorities, and actually browse through that and see what level of risk we were thinking was present in different parts of the country. And we finished up the project with a final conference in Kinshasa that was hybrid in the end, but allowed us to go back to the stakeholders to tell them what we'd done. We also invited a range of scientists from across the country and had a broader discussion on Congo hydrology. So that was all really exciting. And then really we just finished up by then using the data for some FCDO responses, which, as I'm totally out of time, I'll stop there, and if anyone wants to ask about it, please do later.
Great, thank you very much, Jeff. Fascinating, plenty of questions, I'm sure, as well. We'll keep them all. I'll have plenty of time afterwards. Good, thanks. The next speaker is Claire Walsh, but unfortunately she is teaching at the moment, so she couldn't participate in person. So what I'll try and do is share a pre-recorded video of her, which hopefully will come through all right. At least let's try. So hopefully you can see that. If not, someone please stand up and shout. So I'll start that, and I hope that the sound will come through as well.
Right, so I can't hear any sound on this one.
Okay, thank you for letting me know.
Wouter, when you share your screen, I think you can collect, there's a little box in the corner which is also to share your computer sound. So if you stop sharing and then reshare, you might find that you can share your computer sound.
Thank you for that. I'll try that again. And indeed, I see the button share sound. Share. Okay, I'll need to go back then.
Good morning, everyone. My name is Claire Walsh from Newcastle University, and I'm going to give a quick update on the Towards Resilience to Pluvial Flood Risk project. So the aim of this project really was to better understand flooding from extreme rainfall in Kampala in Uganda, to complement and supplement local understanding of this risk, to publish openly available weather data, and to design tools which can help decision makers and the public. So at the project conception, it's identified that higher temporal and spatial weather data would be needed to better understand rainfall events that contribute to flash flooding in Kampala. So early on in the project, we installed 6 weather stations in various locations across the city, including Red Cross offices, residential association offices and a school. So initially these were installed by the research team at Newcastle University and Makerere University, but we also trained those that would be responsible for the stations on a day-to-day basis in terms of how to install them, how to maintain them, and how to download the data and subsequently upload to the dashboard. Some outputs from the dashboard can be seen here on the right, so we can see the location of these stations, plus some graphs that are looking at hourly rainfall over different time periods for the stations. And after a couple of months, it was realised that the data was useful and of interest to the wider communities in which these stations were located. So to better enable communication of the data on the stations, a desktop application was created to enable easy creation of PDF plots, which could then be displayed around offices and schools. So we can see that you can select different periods and different frequencies to create a suitable report. At the centre and the heart of the project really was flood modelling, and we used a 2D hydrodynamic model called CityCat, which has been developed at Newcastle University to understand the areas most at risk from pluvial flooding. We looked at this from a number of rainfall events, sort of rainfall amounts and durations, and here we can see a series of maps showing the number of buildings inundated, given a particular over 30 centimetres for the various parishes across Kampala. Then we use this data, and it could be a number of different types of data. Here we're looking at buildings to see which the most parishes at risk might be, to help hone in on particular areas for the future elements of the research programme. To complement the web app, which I'll show shortly, we also wanted to provide an offline alternative, and the flood maps were created for every parish in a combined document. So we created maps for each of the rainfall events that were just shown earlier. We were able to show the distribution of water depth throughout the hazard zones instead of a threshold, and these maps we were hoping to use in future workshops with the decision makers. So we can look at present key statistics, including the proportion of buildings inundated in each parish and the number of schools, markets, etc. And then, as I say, we ordered them to look at to sort of design the next stage of the project. So an interactive web app has been designed to communicate results from both the rainfall and weather data, as well as the flood simulation. So on the left here we can see the flood risk tool. So we can choose different rainfall events, we can customise the base maps, and we can also decide to include or exclude the effect of green areas in mitigating flood risk, which is a feature of the flood model. Then the depths of flooding of each individual buildings can be assessed for each event, and a heat map can be displayed which highlights flooding hotspots around Kampala. All the source code and data are available on GitHub, and a Docker image which runs the app has been published on the Docker Hub. In addition to the flood simulation results, the web app can display the data collected from the weather stations that have been installed around Kampala. So we have a map of station locations. You can click on the station, isolates the data, gives you a time series plot, and you can look at different frequencies and variables, and again also download that data into CSV files. And then finally, agent-based models, which are useful tools in planning flood evacuation, as they enable visualization and analysis of a range of possible scenarios. So we looked at developed two. The one on the left shows potential routes of evacuation during a flood event, and the one on the right shows agents moving at each time step of a simulation and plots of road usage and evacuation target occupancy as well. So the locations of agents and the number of times rerouted, evacuation status of each agent during simulations are available as downloadable files, along with total numbers evacuated and stranded as well. These hazard zones can be updated to reflect a range of rainfall events and investigate the effects of agents stranded on time taken to evacuate all agents. So we think this will allow good scenario planning based on rainfall events to simulate previous and possible locations for emergency shelters to be identified. And there's also potential to assess the effects on the road network and to identify optimal evacuation routes. Unfortunately, the project was cut short by COVID, and so we're unable to sort of test and these models and tools with our stakeholders and partners. But there was a key and real drive by decision makers, particularly at Kampala Capital City Authority, to explore the use of these tools in helping with their flood risk management strategies.
So thank you, Claire. Unfortunately, no questions for Claire because this was pre-recorded for those that got booked in later. So we'll go straight to our next speaker, Emma B from BGS. Emma, over to you.
Thanks, Wouter. Am I thumbs up? Am I sharing my screen? Can you see my screen?
Yes, it all looks good.
Brilliant.
Yeah.
So my name's Emma B, and I work at the British Geological Survey, and I'm co-PI on the Landslide project. And I'm going to talk about some of the tools we've co-developed to help with better decision making. So first of all, those that might not know about the Landslide project, just to recap on our aims, which was essentially to develop a prototype regional landslide early warning system that combined meteorological and landscape dynamics with social and cultural dynamics as well, in 2 test study areas in India. So by combining these different dynamics, we were trying to achieve some sort of action with impact. So that Venn diagram is important for my slides going forward. So essentially, in hindsight, when I was reflecting on this talk, I was thinking about actually we've developed a number of different tools, and essentially they follow what's called the data, information, and knowledge wisdom continuum. So we've got tools that are part of different pieces of this continuum, where you take data and how you link that to make information. You turn that information into knowledge by connecting some of the dots, the information pieces, which essentially produces insight and ultimately wisdom, which leads to that impact, that actionable consequence of actually doing all of these things. But you need all of those parts of the continuum, and you need to strengthen those different parts of the continuum for the effective decision making, essentially. So the first tool I wanted to just briefly talk about is around data. So ensuring that we had enough observational data, and we left a lasting legacy about collecting comprehensive landslide information and inventories. So making sure that we developed a tool that was both a pro forma, but that was also taken by Amrita University and made into a digital app, whereby people collect data and information. But through co-development, we worked out how we could most effectively and efficiently get comprehensive data from the NGO community, in particular for our project. So we use pictures to represent, size of landslides and so on. So we all, the tools were comprehensive and could, everyone was measuring the same sort of thing in the same way. So that's the data. But obviously, data is needed to turn into information. So we use that sort of information and knowledge about landslides and know where they have occurred in the past to understand, well, why did they occur? What were the geological and geomorphological factors going on the ground, for example? So this is the landscape dynamics element of the project. So we wanted to know, you know, what's the thickness of the superficial geology and what's the land use and so on. So that's information that produces information. And from there, we turn it into knowledge. So in this case, we have a landslide susceptibility map. We know that these landslides are more likely to occur in these types of locations based on the geomorphology and so on. And again, these are co-developed tools with our partners. So that knowledge is also being transferred and people are connecting the dots. Moving on to the meteorological dynamics. I know Joe's in the audience, so I apologise for the very rapid overview here, but it's very similar. There's data, you need observational data, and you turn that into information and knowledge. So one of the tools that our Met Office colleagues in particular were responsible for were our weather regimes work. So understanding which weather patterns in the southern in South Asia would more likely result into landslide events or not, and that gave us a sort of 15-day sort of heads up as to which weather regime was more likely to affect our areas or not. But also through our landslider decider tool, which again said, well, these are the most common weather patterns, and these are the thresholds that are in place given the rainfall. And that produces that sort of information and a tool to give us information about the meteorological dynamics and how they interact with the landscape dynamics. Furthermore, there's the social dynamics element. So again, it's about data, information, and knowledge, but this time it's about how people interact, how decisions are made, and how do we need to, who do we need to co-develop and work with to ensure that knowledge, the scientific knowledge is going to put into action. So thinking about that data, information and knowledge and in these sort of tools here. So institutional mapping was a tool that was developed in the project. Those tools, another tool is really where we start getting the insight. You're bringing data, information, the forecast, the maps, the models that have all been done across the programme, across the project, bring them into our decision support system for effectively our partners at the Geological Survey of India to make a decision about the forecasting of the landslides in our two study areas. So this is bringing those landscape dynamics, those meteorological dynamics and models and systems together for a decision to produce a forecast, and then working with those end users to build that forecast. So this is our tool, which is our experimental bulletin tool, if you like. So using all that information, we're bringing those things together and offering insights. We co-developed the experimental bulletin so that the scientific knowledge that was gained from all the models and the data and the maps was easy to understand. It's in a way that the end users could go, okay, now I understand, and this is what I need to do, or what I might need to do. So again, it's that co-developing that bulletin so that that scientific information is translated and produces that insight. And then ultimately that's that wisdom. So it's the end users using that bulletin to go, okay, this is now what I need to do. And that's the application of knowledge really here, bringing all those parts together and working in a co-developed way to translate that science, that quite technical and detailed science, into something that's useful by non-technical experts, but in a practical and applied sense. And that was, sorry, I didn't realise that was my last slide. That's my last slide. So I put, in terms of impact, I've put a few quotes here. Some of our Indian colleagues gave us some quotes about landslip and what it's meant for them. I won't read them out, but they're there for you, and you can go to our webpage to find out more information. So thank you very much.
Great. Thank you very much, Emma. Again, a fascinating talk. Surely lots of questions. Keep them for a few more minutes until we are at the interactive session, and then hopefully there will be space. But before that, I'll have to introduce myself as the last speaker to present a few slides about the Landslide-EVO project. And I'll try and first share my screen. So my name is Wouter Buytaert. I'm a professor in hydrology and water resources based at Imperial College London, and lead PI of the Landslide-EVO project, which is one of the 4 large consortium projects of SHEAR. The Landslide-EVO was perhaps a bit different from most of the other projects within SHEAR, in the sense that it included research on flooding and landslides and converting that knowledge into actionable evidence for decision making. But at the same time, it also reflected a bit about that entire process of knowledge creation itself as well, as a way to try and think how to improve that, to ensure that it maximizes the local value for decision making. And one way it did that was by looking at the concept of citizen science, which over the last decade has become quite a popular and well-known concept as a way to involve non-academics or non-traditional knowledge creators, if you will, in the process of generating evidence and creating new knowledge. And citizen science is often applied in a very different context. Think about people in the UK going to a park and making pictures of birds, but the idea is to think how it can be, or at least approaches and tools developed in a citizen science context can be leveraged in a context of sustainable development and building resilience in places where resources are scarce and where citizen science perhaps is not yet very much developed and used. And we use this concept of EVO, standing for Environmental Virtual Observatories, as a bit of a catch-all phrase to think about technologies that help with disseminating information, help us with leveraging the virtual environment to create and disseminate knowledge, and basically make that entire knowledge production process more efficient and more inclusive. And essentially that meant that we also did quite a bit of theoretical development and thinking about the building participatory approaches, decision support systems, developing technology that can help with including different types of actors in the production process. So not only decision support systems to convey, to communicate end results, but also as a way to allow people to interact with the different steps of the knowledge creation process. And I don't have the time to go into too much detail, but one of the aspects that turned out to be very useful is the theoretical concept of polycentric governance, which looks at decision and socio-ecological systems as a very distributed system with different centers of decision making, from the classic centers like governments at the national and regional level, but also at a very local scale, how individuals, for instance farmers in the field, to communities at risk of floods, make decisions about how to improve their livelihoods. And the concept of polycentric governance then really allows you to try and think about how those different levels of decision making interact, complement each other, and how to design them in such a way that you maximize complementarity, but also perhaps a bit of overlap, in a way to make the systems more resilient. Another piece of work that we did was through the PhD of Anna Tomlov, one of the SHEAR studentship cohort students, that looked particularly at new ways of visualizing disaster risk and developing a user-centered design framework using an iterative approach to think about how to design visualizations as a powerful way of communicating risk to different types of end users, and how to tailor that really to the type of end user that will be using that information. So that's the theoretical bit. Then the project also worked very practically on tools and methods that can help with improving participation of non-scientific stakeholders. And there we did a lot of work on developing new technologies, and particularly leveraging low-cost open source technologies to build robust sensors that can be used to measure things like water level as ways to improve and support community-based soil early warning. And so there we did a lot on developing those technologies, and again implementing an iterative approach to developing sensors that generate the right information, but they can also be used by local people and local groups that don't have a formal training in electronics or environmental sensing. And all that is available on GitHub, the code itself and the blueprints, but also different ways of training materials, from videos to manuals. And the same about visualization and processing information. Also there, the project did a lot of work on developing an open source hydrological data management platform. Again, working very iteratively with local end users, but also local developers, particularly the company called Kathmandu Living Labs that provided different open source toolboxes of visualization and data processing that are now being incorporated in various operational workflows in Nepal and India. And that's all very quickly what I wanted to tell about Landslide-EVO project in a bit of a whistle-stop tour with the idea of keeping the last 10 minutes free for discussion. So now we move on to the interactive part, and as I mentioned at the very start, feel free to ask questions to any of the presenters, but also please do use the opportunity to flag any relevant experiences and activities that have happened within the much broader realm of SHEAR. We definitely don't want to constrain it only to the presentations. To keep things manageable, please do raise your hand through the Zoom. The Zoom interface. I hope you know how to do that. Click the button reactions and raise your hand, and I'll then moderate, pick them up, and give you the floor to ask questions or present any other research and ideas. I try and take hands as they are raised. I see Ting, so Ting, over to you.
Thanks very much. What's actually a question for you? So you mentioned this visualization framework to improve the communication of hazard risks. Can you tell us a bit more about that? I'm quite curious about that. Thanks.
Yes, so here we try to use or to leverage some of a lot of the work that goes on in terms of building what are called infographics, detailed, rich visualizations, if you will, of information related to resilience and risk. And so the idea here was to try and look a bit into almost the psychology of visualization and understand what is the right level of complexity that visualizations need to be pitched at to make them useful for different audiences, recognizing that obviously if you visualize for a local community member, the type of visualization you need is very different from a professional decision making maker. So understanding how that process of tailoring needs to be implemented to maximize the relevance and the conveyance of information. And so what Anna did was develop a theoretical framework of the different steps of developing a prototype and then interacting, touching base with an end user, the type of questions that you need to, or you can ask to generate the right level of feedback that can help you then go back to with the designer. So she basically tried to come up with a system where on the one hand you've got a professional designer that knows the theory, if you will, and on the other hand the end user, and how you switch back and forth between those two to gradually refine a visualization for the right audience. And the work is currently under review, and so hopefully will soon be published, and I'd obviously be very happy to share it with anyone who's interested.
Great, really looking forward to reading that paper.
Thanks. You. more questions or comments or ideas, please do stand up. I hope that everyone has the possibility of switching on their microphone and video through Zoom. We've got about 30 participants, so I'm sure that there are other thoughts and experiences from the audience. We're waiting for more hands to be raised. I'd be keen to. I think, is that your hand again, or?
Yes, that's my hand again. Can I have one more question here?
Yeah, please do. Yeah.
Actually, for Jeff. It's amazing to see over the years your modeling capacity in terms of resolution is increasing. I'm just wondering that for such improvement, which technique is most important to contribute to such improvement? Remote sensing or modeling scale or whatever? Thanks.
Yeah, it's a good question. To be honest, the principal improvement that's allowed that is the change in the digital elevation data. So the original data set was largely SRTM based. The second one also so, but was the Merit DEM that was developed by a guy called Dai Yamazaki at University of Tokyo. The latest version is a forest and buildings removed version of the Copernicus DEM. So taking the Copernicus DEM, which is essentially Tandem X remote sensing data, and we've removed the forests and the buildings from that data set to create a digital terrain model at 30-meter resolution. And actually, we just published a paper on that. It's called FabDem. It was out last week. And if you want to take a look at it, you can download the data off the University of Bristol's data server. And so that's for the whole globe. I think that's been the major advancer. I guess the next one will be if we ever manage to get global photogrammetric DEMs from high resolution stereo pairs, then we'll see a further advance in these kind of global digital elevation models. Lots of other little things went on, but that's the big ticket item.
Great, thank you very much. And I'll have a read until your latest paper. Congratulations, Andrea.
Thank you.
Thank you.
Thanks, Jeff. There's a question in the chat from Waldo Lavado. He asked, what is the difference or relationship between climate services and the activities, these interesting activities? I suspect that that he refers to the activities that have been presented in this session. Yeah, so that's basically Waldo's question. How the activities within SHEAR relate to climate services, or whether any of the speakers considers the type of products and tools that they've generated are part of the broader idea of climate services. Any one of the speakers or anyone else who's keen to give a view on that question?
I think I can go for it.
Yes, Emma, please do.
I think looking at, for example, the work we did under FOCPAC, it contributes to climate services within Kenya. And why I say so is because one, the meteorological department within Kenya was a partner in the project. And once the new actionable products were co-developed, they were taken up by the meteorological department and now are part of their seasonal forecast bulletin, just to inform drought management in Kenya. So working with the mandated institutions, if they're able then to take that and sustain that, then it becomes part of climate services within the country. But it's also a question of the demand from stakeholders. I think it's also if the stakeholders that people worked with in the projects are able to push for the sustainability of this, then they can be incorporated and become part of climate services within the countries.
Great, thank you very much, Emma. Good, with that, I think we're running out of time. So just seeing whether there's any last hand or comment from the audience. But if not, then given that we've got only a short break of 15 minutes before we start again, I don't want to encroach upon your lunch break. So instead, I just want to finish with thanking again all the speakers and the questions that were asked. So thank you very much. Hope you enjoyed the session, and we'll see you all again in 15 minutes in the